So today we'll start or we'll discuss about the today we'll learn about the thyristor control reactor. Actually it is a SVS only. So last class what we have learned is we have learned about the SVS stator var system, right? So under that we have seen that different types of SVCs. Okay, so there are different types of SVCs. So from that I will choose only two. One is thyristor control reactor, TCR, okay, and another one will be TSC. Okay, later on tomorrow we will learn about the TSC, that is thyristor switch capacitor. Okay, so I will take only these two and then we'll see how these two SVCs can control the voltage. And so when we control the voltage, it is controlling the reactive power, right? First reactive power has to be controlled, then only it will control the voltage. Okay, so last class we have learned about the SBS. So and then for today we'll see about the TCR, that is thyristor control reactor. And then I have also said, okay, to you all that please study about the synchronous condenser, since it has been learned in machine, so it remains safe. Okay, so that one note I have uploaded. Okay, so you can just download and see that. Okay, so today we will see about the thyristor controlled reactor, TCR. So first we'll see what is meant by TCR. Already you know that what is meant by SVS. Actually it is just like simple inductance and capacitor. Reactor means it will be inductance, but it has been connected either in parallel or series, and then eh, they use for observing and injecting the reactive power. So that is known as SVCS. Actually, all principle we know, but today we will see one additional device, that is thyristor, which means we will use another component or device, thyristor. Okay, so you know the properties of thyristor, so which we can control its firing angle and conduction can be controlled there, right? So whereas if you use directly a reactor, we will not be able to control. Okay, but if you use the thyristor, then it is like a switch. Whenever required, it will be switched on, and whenever it is not required, it will be switched off, right? So based on the firing angle and all, so we'll see that. Okay, this is just an introduction of the thyristor control reactor. So then you know when you will use a reactor, when there is capacitive in nature, right? We have to observe some reactive power. So in such case, we'll use this. If you are required to inject the reactive power, then this thyristor control reactor cannot be used. Instead, we'll use another device which we will learn tomorrow. Okay, so before we start, so first little bit of basic principle of operation we'll go through, but detail you will learn in power electronics application. And then I had discussed with your module tutor, and he said, so detail, I think today or tomorrow he will teach is all principle, working principle detail. Okay, so don't worry about this, but today just I will touch the little bit of working principle, and then you might have even introduced in power electronics. So first we'll see how it operates. Okay, principle of operation of TCR. Okay, so now, so see that figure A. Okay, so you can just see this figure A, or figure A, basic element of thyristor. Okay, basic element of TCR, thyristor control reactor. So if you see here, you can, we may get shocked also here. What you have is, there is no other device. Okay, but name says it is very like a sophisticated one, thyristor controlled reactor. So that this concept, this has been connected to the switch. That switch is a thyristor switch, so it make it a TCR, right? So, but if we see that name TCR, thyristor control reactors, we may feel that it is like a very complicated device. But if you see this figure carefully, you can see that there is only one inductors, or we call it as a reactor, and then two thyristor. or switch. Why we are using this thyristor? To control your conduction or by giving certain firing angle, which you have learned in the power electronics, right? So it does not have a complicated equipment as such. So now you will know that working principle of this one. Okay. So during positive half cycle, so let's say during positive half cycle of your input voltage, what it will happen is, so this thyristor will be in the reverse bias, which means current will not flow from here. Instead, it will flow from here. So now I will explain with just naming this. Let it say T1, other one as a T2. Okay. So during positive half cycle, okay, so during positive half cycle, so thyristor T2 will be in the reverse bias, thyristor T1 will be in the forward bias. So it will conduct from T1 like this. Okay. Similarly, during negative half cycle, okay, what it will happen is current will flow, T1 will become reverse bias, T2 will be in the forward bias. So your current will flow like this through T2, and then this. Okay, this is a basic working principle. Okay, so but in detail, all derivation and all you learn in power electronics application. But here we are focusing towards the controlling, how to control the voltage. But before we control the voltage, it is good to know a little bit or revise little bit of the uh, working principle or principle of operation of thyristor control reactor. Okay, so now I will explain once more with respect to this figure A only, figure 1A. So now TCR means one inductors connected in series with these two switches, thyristor T1 and T2. It is known as TCR, thyristor control reactor, because this is inductor is, we call it as a reactor, and then we use this switch to control the flow in the reactors. That's why it is called it as a thyristor control reactor. Okay, so now how it works during positive half cycle. So let's say this one be at T1, other one be at T2. So now during positive half cycle, T2 will be in the reverse bias, T1 will be in the forward bias. You know that. So it will flow from T1 like this. During negative half cycle, so now T1 will be in the reverse bias, T2 will be in the forward bias. Then again it will flow like this. Current will flow like this. Okay, so this is a just basic working or operation principle of TCR. Okay, so everything I have explained here, or if you are not able to, you are not required to memorize all this. Okay, you can just explain like this. If somebody asks, what is the working principle or principle of operation of thyristor control reactor? So you can say positive half cycle, it will be flow like this, and then negative half cycle, and just draw this one. Okay, so now why it has used a two thyristor? Okay, so why we have used a two thyristor, why not one? This is because, so if you use only one thyristor, so what it happen is only you will be able to control or conduct only in the positive half cycle. So negative half cycle completely blocked, means your waveform will be just a straight line. But thyristor conduct on to have an alternate flow in the half cycle. Okay, so in a positive half cycle one flow, in negative half cycle another flow, which means it is a full, right? So thyristor conduct on alternate half cycle of the supply depending on the firing angle. So I have not explained about the firing just now. What I am saying is during positive half cycle it will be flow like this, and the negative half cycle it will flow in another way. Okay, so now we have to go a little bit of this property now, thyristor. So it is not a simple diode. Thyristor is, it will have three terminal, anode and cathode. At the same time it will have a gate. Okay, so this one is a gate. So now why we use a thyristor is, so as per our requirement we can fire this thyristor and then make, even if it is a positive half cycle, so if you are not fire this gate signal, then you will not be able to flow the current. Current cannot flow if you are not fire. So now what it says is, now we use this thyristor and then we'll make it to pass the current in the alternate cycle depending on the firing angle. So now firing angle, normally it will be represented by alpha. So now firing angle, how to choose firing angle is depending on our requirement. So now that's why it is written firing angle alpha, which will be measured. Okay, so now if you observe properly, so now we will not talk about the voltage. When voltage flows, so definitely current will be flowing. But for us, let's see with the example of current. Okay, so now what it happen is, so now here you know that current is lagging behind the voltage with this waveform, right? See here, lagging by 90 degree. Okay, this is voltage and then this is current. You know why it is lagging, because it is a reactor or inductive load, right? So current will be lag. So now you see that properly. So what it happen is, in this thyristor, okay, conduction take place with a firing angle of 90 degree. If you fire at alpha equal to 90 degree, you can see from this waveform that it will be conducting. Okay, full conduction will take place. Full conduction is obtained with a firing angle of 90 degrees. So if firing angle is 90 degree, you can say that during full conduction is taking place. And then current, normally it will be in the form of sinusoidal. Okay, it will be in the form of sinusoidal, and then we call it as essentially reactive and sinusoidal now. Okay, so now what it will do is, if you try to increase the firing angle alpha to, let's say, 90 plus, okay, partial conduction is obtained with firing angle between 90 to 180. So now let's say this is a 90 and this one is 180 degree. So now if you fire between these two, so now full conduction will not take place, because we have just given a gate pulse or signal from here. Let's say alpha equal to 100. Okay, so which means, so now it is not conducting full, right? So this portion has been chopped off. See here, here alpha equal to 100 degree. So which means actually full conduction means it has to start from here. But what it happen is, okay, so this portion, okay, this portion has been chopped off, which means full conduction is not taking place. Instead, partial conduction, still conduction is there, right? But if between this 180, 90 and 180 degree, but if firing angle is 180 degree, then during positive half, there won't be any conduction. Whole it will be cut off like this, right? But which is not desirable one. Which, why we are using this firing angle is based on our requirement, at what angle you have to fire, and then all we have to know this, right? So that's why we are using the firing angle concept. So now if you fire at 90 degree, so full conduction is taking place. Okay, then this A, we have seen that alpha equal to 90 degree, so full conduction starts. So now how you are getting 180 here. Okay, so that sigma is a conduction angle. Okay, so this sigma is a conduction angle and alpha is a firing angle. So now if you fire at alpha equal to 90 degree, then you are getting full conduction, which is equal to 180 degree, because so actually your cycle start, okay, 0 to full cycle means 0 to 360, right? But it has been fire at 90 degree, and then your current start conducting there. Okay, but it has to end at 360 only, right? So what you get is, it's a full cycle, it will be 2. Okay, so that's why you will get conduction angle to be 180 degree. Okay, 90 into 2, actual cases what you have to do is 90 into 2. Okay, 90 into 2, that is 180 degree, then sigma will be equal to 360 minus your conduction. Okay, so which will be equal to 180 degree. 360 minus 180 is 180 degree only. So similarly I will explain with another one. Okay, so this with firing angle equal to 100 degrees. So now if firing angle is equal to 100 degree, so now your full conduction should be, okay, alpha equal to 100 degree. So what you will have is into 2 we have to do because this is for full wave, so it will be 200. This is a firing angle. Okay, so you are firing at one at the 100 degree, another one at negative half cycle, so you are firing at the 200 another 100 degree, which means it will come 200. So now your conduction will be sigma equal to 360 minus 200 will be equal to 160 degree. Okay, so similarly you will have here, okay, if you fire at 130 degrees, so you will get 100 degree. It's a conduction, so don't mix up with the alpha and then sigma. Okay, so now conduction has been represented by this sigma, whereas uh, firing angle has been represented by alpha. So now if you fire at 90 degrees, so their full conduction is taking place, and then if you fire at 100 degree, so your conduction is 160 degree, and then if you fire at 130 degree, your conduction is 100 degree. Okay, so that's about the basic principle of operation of TCR. So now little bit of the derivation will start, but I will not explain in all detail about this one. So please refer to power electronics application. If you have not learned, so definitely sir will teach about this all in detail, okay, with derivation and all. Okay, so but just now what we will do is, so we will just assume that let conduction angle sigma be related by this basic equation. How it has been related, so you will learn in the power electronics application. Okay, so don't worry about this. So now sigma is given by 2 into pi minus alpha. What is sigma? Sigma, it is a conduction angle. Okay, let it be equation number 1. Then if you consider this conduction, then instantaneous current I is given by this basic equation. Okay, instantaneous current I is given by I equal to, so under root of 2 V by XL cos alpha minus cos omega t. How you are getting this all? So don't worry here. So you can go through the power electrons application. But when you will get this is, there is two options. When alpha is, that firing angle is less than omega t, less than alpha plus sigma. Okay, and then it will be 0 for alpha plus sigma less than omega t, or in the range of alpha plus sigma to alpha plus pi. So this one you will get from this basic equation, sorry, waveform. Okay, so this waveform you will get the basic current equation of this one. So it will be given by under root of VL. So cos alpha minus cos omega t, where alpha, okay, in between alpha, actually this x-axis will be represented by time axis, that is omega t, and then this one will be current if it is voltage V, y-axis. So now it will depend on alpha to alpha plus sigma. So how much it has been done. Okay, then rest will be 0. Okay, so that's why it has been written alpha plus sigma to alpha plus pi. So again here we will have pi, but alpha firing angle will start. Till then you will get a 0. Okay, so that's how we got the equation. But how you have got this all, so please you will learn in the power electronics application. Okay, just now you know that conduction angle is related by sigma equal to 2 pi minus alpha. Then if it is related like this, then instantaneous current I will be given by this equation, basic equation, for alpha less than omega t less than alpha plus t, and a 0 for s. And so now here you have to apply. So next time I'll give an assignment. Okay, so here I'll take it this one only. So you have learned in mathematics, if you have this type of equation with this condition, you can carry out the Fourier analysis, Fourier transform analysis, and then after carrying out the Fourier transform or Fourier transform of Fourier series analysis. Basically, this will be a Fourier series analysis. So of this current waveform, and it will give a fundamental equation I1 by equation number 3, which I1 is equal to V by XL sigma minus sine sigma by pi. Okay, so if you carried out the Fourier series analysis, so you will get series means you will have a, just I'm giving I1. Okay, so I will just explain in terms of this. So let's say Fourier transform of current I will be equal to I1. You will have I1 plus I2 plus I3 and then so on. Okay, you will get like this. Okay, it will go like this Fourier series, and then we consider that first one as a fundamental. So here we are not using all other component of the Fourier series. We will take out only the fundamental component, so which you have done in the mathematics. Okay, so now if you carried out Fourier series analysis of this equation number 2, all condition is known, so you will be able to perform that. Then you will get the fundamental current, or give the fundamental components. I1 will be equal to V by XL sigma minus sine sigma by pi. Okay, so how you have got this? After carrying out the Fourier series analysis of equation number 2. Okay, so where I1 and V are the RMS value. Okay, we have to know that it is RMS value. XL is the reactance of the reactor at fundamental frequency. So this is the basic equation, but how you will get this all equation number 1 and 2. So you learn in power electronics, and then I1 so you have already learned in the mathematics Fourier series analysis, Fourier analysis they call. Okay, so I may give some assignment later on to carry out this Fourier series analysis of equation number 2. Okay, so these two you will get already, you have learned, and other two you will learn in the power electronics application. So but just now you know that conduction angle and then instantaneous current. If we carried out the Fourier series analysis of equation number 2, then we will get the fundamental component. Okay, current waveform gives the fundamental component I1, which is equal to V by XL sigma minus sine sigma by pi. And then you know what is I1, what is XL, V, and then all. Okay, so this is a basic now. So now what you can see is using this all basic. So we are, as of now, we are not controlling the voltage. What we are doing is just we are trying to see the fundamental component of TCR. Okay, so now little bit of derivation and then all we have done. Detail you learn in power electronics application. So now what you can see is, you can see clearly this. If you increase the alpha, so here from this diagram itself we will know that alpha 90, your sigma is 180 degree conduction angle. When you increase the alpha 100, your conduction angle is 60 degrees, 160 degree, which means decreasing. Now when you increase to 130 degree, your conduction angle is 100 degree. It keep on decreasing, right? So this just I'm saying effect of increasing alpha. When you increase the alpha, your conduction will decrease, conduction angle will decrease, and then it will reduce the fundamental component. So definitely if we substitute here that fundamental component I1, okay, I1, so you will get a reduction. Okay, so reduction in component. Okay, so what it means is if you reduce this is equivalent to increasing the effective inductance of the reactor. So if you are able to reduce if you are increase the firing angle, your conduction angle will decrease. When it decrease, so it will reduce the fundamental component I1 after carrying out the Fourier series analysis. Then what it indicates is this will increase equivalent to increasing the effective inductance of the reactors. So why we are employing TCR is when there is over voltages, right? Means we have to observe the reactive power and then bring back. So that's why we are trying to increase the inductance. Okay. So what it means is, in effect, as far as the fundamental frequency component is concerned, is TCR is a controllable susceptance. So we call it as a, so is TCR is a controllable susceptance. So you know that it is represented by B, and then you know that reactants and then susceptance, right? Difference between these two. Okay, so unit of susceptance will be mho or inverse. Everybody knows, right? So now effective susceptance is given by, okay, firing function. If you want to express this susceptance in terms of firing angle alpha, so you will write B. Normally it will be represented by B will be equal to I1 by V. Actually it is I, but we are trying to find out for a fundamental component only. So that's why we have taken I1 by V. Okay, so you try to get the earlier equation. So if you bring this, arrange this, then you will get I1 by V equal to sigma minus sigma sine sigma by pi XL. Okay, so you know that actually if you are required to find the impedance, it is V by I generally, but susceptance is a reciprocal of this impedance. B will be equal to 1 by Z, which will be equal to I by V. Actually this is how we got this, but I1, so here we are focusing towards the fundamental component, so that's why I have written I1 by V. Okay, so this is a basic relation. So but if you are not able to get this, so now you go here. Okay, so you go to this equation and then you see that if you bring here, okay, so if you just arrange this here, I1 by V, and then you will get sigma minus sine sigma divided by XL pi XL. So this is known as a susceptance. Okay, so from here also you will get, but you know the basic equation which I have given now, right? So now what you know is we have assumed that conduction angle alpha is equal to 2 pi minus alpha. So that's why I have written 2 pi minus alpha. So now similarly you will get sine 2 alpha. Okay, other thing remains same. This one just I have substituted for conduction angle, but how you have got 2 sine alpha from this sine alpha. Okay, so you know that sine, okay, alpha is given by this, sorry, not alpha, sigma, that is a conduction angle, is given by 2 pi minus alpha. This is a relation which we have considered in the equation number 1. So now just substitute here, okay, just on this. So 2 into pi, so normally we can write as a 180 minus alpha. So then you know the basic relation of the trigonometric sine 180 minus alpha, sorry, not alpha here, because we have to open this bracket, 2 alpha. So it is written as sine 2 alpha. This is how we have got here. Okay, just substitute the conduction angle. Okay, 2 pi minus alpha, and then if you substitute and then rearrange using some basic trigonometric relation, then we will get sine 2 alpha. Okay, so which I have explained here. Okay, so you will get this. Okay, these are the basic, okay, basic equation. So now if you see carefully on this equation number 4, so what it happen is, if alpha equal to 90 degree, okay, so if alpha equal to 90 degree, so your, okay, conduction angle should be 180 degree. So okay, so theoretically it says when alpha firing angle equal to 90 degree, then your conduction should be full 180 degree. Okay, so now what it says is, so now if alpha equal to 90 degree, so you substitute in equation number 4 90 degree. Okay, so now sine, okay, so now here you can write pi minus 90. Okay, so now you substitute 2 into pi minus alpha is 90, we have considered, plus, so here it will come 2 into 90 is 180. So sine 180, what is the value of sine 180? So you know that pi. So if you substitute that, then you will get a maximum value of this B susceptance, which will be equal to 1 by XL. Okay, which will be equal to 1 by XL, and then minimum value will be 0 when alpha equal to 180 degree. So you substitute here alpha equal to 180 degree. Okay, so if you substitute alpha equal to 180 degree, then your conduction will be equal to 0. Okay, so that's why theoretically I have mentioned that, right, in the beginning. So we have started with this. Okay, so now what you can see is, so we have completed the basic operation, principle of operation of the TCR, terrestrial control reactors. Okay, so now we will go see how we can control the voltage, okay, in a line applying this TCR. Okay, basic principle we have known that. Okay, so now using this one, so we have to control the voltage. So this one is very important in our module, power system operation and control. Other one, okay, this all you will learn in the power electronics application. But so I have given some basic theory about the principle of operation of TCR. So using this principle and the concept, so now we have to see how we can control the voltage. Okay, so how we can control the voltage, so we'll see that. Okay, so now see here, you know the VI characteristic. Okay, so VI characteristic of our SVC. Okay, so we know the VI characteristic of the SVC, and then this TCR is one of the SVC. Okay, so this TCR is one of the one type of the SVC. So now using this characteristic, how we can control the voltage. Okay, so here I have written VI characteristic is shown in figure 2. Okay, fundamental voltage current characteristic of a TCR is shown here. Here in terms of per unit I have shown. Okay, so per unit fundamental current in the x-axis and the y-axis you will see voltage, both are in per unit. So now you know that this one is a, we have learned that this similar to same as the SPS characteristic. Okay, so this one is TCR characteristic. Okay, so which means SVC characteristic, and then other dotted line, this one, the horizontal line is a, let's consider it as a system characteristic, means power system characteristics. So now this will be based on this, so we can derive one equation. So what you will get is voltage, you can find out voltage V, okay, by this relation, which will be equal to reference voltage plus this XSL into I1, where XSL it is a slope reactance determined by the control system. Okay, so it's a slope reactance. So now you can find V equal to, okay, so this can be represented by V equal to V reference plus XSL into I1. What is I1? It's a fundamental component of current, and then V reference. So normally reference we will keep it as a 100 or 1 per unit, and then we can find the voltage, means how we can control the voltage. So now if you're able to control this, and then if you bring this characteristic to this dotted line, then we will be getting constant voltage. Okay, so 1, or if it is 400 volt, then we'll get a 400 volt on. But in actual case, so there will be some, okay, acceptable limit. Okay, so now if you go beyond the acceptable limit, then we have to control that. Okay, so now let's assume okay, now let's consider that. Okay, so uh, okay, so first let's start from here. We reference, and then this one you have to know that it is not a firing angle. This all 0 degree, 90 degree, 150 degree, and 180 degree is a conduction angle. So when you will get 0 degree, when you will get 90 degree, when you will get 130 degree, 150 and 180 conduction angle, you know that at what firing angle you will get this one. Okay, so already I have explained. So now how we can control the voltage? Now for this VI characteristics, so we will get a basic relationship V equal to V reference plus XSL into I1. So now V reference, we normally will get at 1 per unit. Okay, 1 per unit. And then based on this fundamental current and a slope, so now we can control the current. Sorry, not current. We can control the voltage. Okay, so now how? So let's start with this basic one. Okay, so now initially you have a conduction angle 0. It's fine when it is 0. So you are getting exact voltage, that is 1 per unit. Okay, so then what you can see is as conduction angle increases, okay, as conduction angle increases, what you are getting is your voltage variation also increases, right? See here, reference plus your this slope, we have to see that, and to I1, so your voltage will keep on increasing. So now based on our requirement, if you are required to maintain at 1 per unit, then as far as possible your conduction angle should be maintained at 90 degree. Okay, 90 degree. And then if, okay, acceptable range might be, so 1 per unit is a nominal one, but there will be a plus minus 5%. Okay, let's assume that the acceptable range is plus minus 1 plus minus 5% is, so now you may get this much. Okay, this is an acceptable limits range, let's consider that. So now when we cross here 130, so at least your voltage will be at the acceptable range. But when we cross your conduction angle above 130 degree, what it is happening is now it is going to over voltages, right? Which is undesirable. Now how to control that is, so now you use this TCR, and then for TCR, so at what firing angle you have to make, provide to get a conduction angle 130 degrees. So you can do this. Okay, so that's how we can control the voltage. Just now I have given example 5%, so acceptable range might be more also, right? But we have to know that at what conduction angle is our voltage will be in the acceptable range. Because if you're able to control this I1 and the XSL, then we will be able to, if you're trying to maintain this at the zero, then we will be able to maintain at the nominal voltage. But so in practical case it is impossible, so there will be a, that's why it has been mentioned that in every equipment plus minus will be there, your voltage. If it is written 230, sometimes it may cross to 230, 240, and then below that also, right? So this is a reason for why it has been mentioned plus minus. Now if it cross beyond this 240, then it is called it as undesirable voltage. Now how to control is, you apply this TCR and then fire the TCR. So let's say if this one is an acceptable one, 130, then fire the thyristor of a TCR at the required firing angle, and then make the conduction angle 130 degree, then it will be at the desirable or the required or acceptable range of the voltage. So such type of control, okay, so such type of control or certain principal control is known as phase control. Okay, this is known as a phase control. So similarly, now I will explain in another way now. So now let's assume that this much voltage, over voltage has been taken place. Okay, so which means if it bring back here, so let's assume that it is 1.1. Okay, so 1.1. So which is not acceptable. Okay, so voltage is going beyond your acceptable range, 1.1. So in such case, so now what you can do is you employ the TCR and bring back to either to 1, okay, this 1, or to the acceptable range which we have considered as 130 conduction angle. So now how we will bring this is, okay, how we will bring the or to the acceptable range is, you have to apply the TCR when there is over voltage taking place, when load is in the capacitive in nature, right? So now what we have to do is, so we have to employ, okay, so let's say this is, we want to maintain at reference voltage 1 only. So now what you can know is this much. Okay, so we have to consider from here this much inductive you have to employ, and then observe the observe the reactive power. So we have to employ this much XL. inductance and observe the reactive power, so that it will be bring back to the reference voltage. Okay, are you getting now? So this about the this about the principle of operation of TCR and how it control the voltage. Okay, so next we will see on harmonics, even though it is not in the syllabus. So we'll try to see a little bit on the harmonics also. We have not considered about the harmonics. Harmonics is also another problem in the transmission line. Okay, so harmonics. Okay, so this harmonics actually we know that as alpha increase from 90 to 180 degree, okay, the current waveform will become less and less sinusoidal. Okay, what it means is if it is a purely sinusoidal, then it is good. Okay, but if it is less, becoming less and less sinusoidal, means some distorted waveform you are getting. So what it means is if you are getting in that form, then it is known as TCR will generate the harmonics. Another problem with, so that's why we cannot employ the TCR. Okay, or we, if we employ, we have to know certain limitation is there. But if you find that your current waveform is becoming less and less sinusoidal, it means that TCR is generating harmonics. Then harmonics is another problem of the power quality. So we will not be able to maintain a good quality if there is a harmonics generation. So now what we have to do is at the same time, we are able to control the voltage, but if you use this TCR and then if it found that your current waveform become less and less sinusoidal, then harmonic is generating there. So now we have to filter the harmonics. So now how you will filter? You know that by using a capacitor or filters are used to remove the harmonics. Okay, so now what you can do is there are different ways which we can remove the harmonics. So first figure A, there are an 6 pulse TCR can be used to remove the harmonics. Okay, so here it has been written for single phase device. Okay, so till now I have explained in terms of single phase. If the firing of a thyristor is symmetrical, means equal for both thyristor. If you fire at the equal firing angle, then it says only odd harmonics are generated. Okay, so only odd harmonics are generated. And then so basically for a three-phase arrangement, okay, so for three-phase system, preferred arrangement is to have the three single-phase TCR elements connected in delta. So these three TCR connected in delta, okay, connected in delta, we call it as a 6 pulse TCR. We will try to connect this and it will try to remove the harmonics. Okay, so we'll arrange this TCR, but in three phase we can connect. In first option is this figure a 6 pulse, okay, connected in the delta. Okay, so if you connect like this, what it will get is in balance condition. We have to consider it as a balance condition. All triple, that is 3 9 harmonics circulate within the closed delta. All harmonic will be circulate within this delta and therefore absent for land. So now it will try circulate in only in this TCR, okay, and then it will not supply to the line. So this is how we can remove the harmonics. Okay, here why we require a controller is because we have to control the firing angle. We have to say that it has to fire at alpha equal to 90 degrees. So that's why we will find the control circuit here. Okay, so one way how we can remove. So in such case, if you arrange like this, all triple, that is 3 9 will be removed because all harmonic will be circulating this delta only. Okay, but again we here in this problem is only triple one will be removed, but another we have no fifth order, 7 order, 9 order can be removed, third order can be removed by connecting like this in figure A. Then problem is we have fifth order, then 7 order, 11 order harmonics will be there. Right? In such case, how to remove this is by using another concept, that is 12 parts TCR. Okay, so we can use this 12 pulse TCR, but here will not connect directly to the line. Instead, we will have a transformer in the 12 pulse TCR. Okay, so in this one, so you can see that similarly here control signal is for providing the firing angle and then control this. So now what we will do is, so using these three, okay, for these three, okay, with these three arrangement or 6 pulse TCR, we can remove this triple 1, 3 and 9. But so another problem is we have fifth and then 7 order. Okay, so in this case, how you can remove is elimination of fifth and 7 order can be achieved by using 2 6 pulse TCR. That means actually we are combining this one TCR, but it is known as 12 pulse arrangement of equal rating fed from two secondary winding of a step down transformer connected, one in the Y star and another one in the delta. Okay, so delta, okay, delta as shown in this figure, right? So we have I have shown here 12 parts to remove the fifth and 7 order. Okay, so third and 9 order it will be removed by 6 pulse. Okay, so here also we have 6 pulse. We are connecting 6 pulse to make it 12 parts, so that we will remove the fifth and then 7 order. Okay, so now since voltage applied to TCR have a phase difference, in this one phase difference will be equal to how much? 30 degree, right? Each TCR will have a 30 degree. 30 into 12, how much we will get is 360, right? 30 into 12, it is a 360. So means each TCR will have 30-degree voltage difference, and then if you add up for this 12, so what you will get is 360. Okay, so we want 360 degree. So in such case, so what you can do is, see here, since voltage applied to TCR have a phase difference of 30 degree, fifth and 7 orders are eliminated from primary current side, which means, so now we have, okay, so in the 12th or pulse arrangement, each TCR have a phase difference of 30 degree. So if it is 30 degree, then your fifth and 7 order harmonics are eliminated from the primary side of the current only. So from here primary side itself, it will be remove harmonics. Okay, so now what it has been left is we are able to remove the third 9 order by 6 pulse arrangement. Then if you are able to carry out the 12 pulse arrangement, then we are able to remove the fifth and 7 order harmonics. So now only we have left is, okay, left is 11 and 13. So other all has been removed. So 11 and 13 has become the lowest. Okay, so it has become the lowest. Okay, so please wait. Okay, so actually Roshan is asking some question. Okay, so later on I will explain this one. Okay, first listen about this. Okay, so this is known as 12 parts arrangement because there are 12 thyristor, and then using this, employing this 12 parts arrangement, we can remove the fifth and the 7 order harmonics, and then lowest one it has been left is 11 and 13. So this 11 and 13 can be removed easily with the help of simple capacitor bank. Okay, this is how we can remove the harmonic. Okay, so now I've got one question. So okay, so Roshan is asking his question. What is third, 9 feet and 7 order harmonics? Okay, so he is asking about, actually I assume that you have learned something about the harmonics, so you have not learned about the harmonics. Okay, so if you have not learned about the harmonics, so normally you will have a harmonics. Okay, so harmonics actually it is a disturbances, and then you will have a harmonic of, actually you will not have harmonic even harmonics. So most of time you will have harmonics in the odd numbers, that is third or first, second won't be there, third, 4 is not there, fifth 6 even it will not be there, 7 8 is a even one, so 9 11, then 12 is a even number, then 13 actually it is a harmonic in order which harmonics occurs. Okay, so normally it will in this odd harmonic means which is not able to cancel each other. Okay, so even means if there is even harmonics, so it will cancel each other. But so odd we will not be able. Okay, so two can be cancelled, but again one will remain, third one. So which means third harmonics. That's why it is called it as a third harmonics. Okay, so in third harmonics, third, fourth, fifth, actually it is the order of the harmonics. Okay, so as per your question, it's asked that what is third, ninth, fifth, and then seven order harmonics. Actually it is a when you talk about the harmonics, so there will be order third, third, fifth, seven, and nine, and this is actually an order of the third harmonics. Based on the order of the harmonics, severity of the harmonics will be there. Higher the order, okay, so your severity will also be higher. Okay, so harmonic. Okay, so if you have not understood about the harmonics, so here actually it is not in the syllabus as such, but I thought employing this TCR will create a harmonics. So now if you know about how to remove the harmonics will be much better, but it is not in the syllabus, it's fine. But later on, if you want to do a research, so they will ask to remove the harmonics also. So now if you have not learned about the harmonics, so now I think power system stability and design, so at least harmonics should have been learned. If it is not in the syllabus, try to see that in the Google, type that what is harmonic first, and then say that what are the different orders of harmonic, and then also try to find that severity of harmonic. So there are third order, fifth order, seventh order, and eighth order. Actually, it is an order of the harmonics which we consider. Okay, so and then this how we can remove is, so actually this simple way which we can remove is just rearrange the TCR. Okay, 6 pulse TCR can remove the triple one, third and ninth harmonics, whereas 12 pulse can remove the fifth and seventh order. So if we are able to remove this, then we are left with lowest harmonic is 11 and 13, and then this one can be filtered with the help of simple capacitor bank. So if you have forgotten, okay, actually at least you might have learned in analog and digital electronics practical, so how to employ the capacitor to remove the harmonic. So when you employ the capacitor, you might have seen that your waveform get smoother and smoother, not a distorted one. Okay, so this one you might have observed, but they might not have taught as a harmonic, but they might have taught it as how to improve the waveform. Okay, so this is little bit on the harmonics. And then so last topic is about the dynamic response, how this TCR will respond. Actually it has to respond in about 5 to 10 milliseconds, which means if there is over voltage, so immediately within 5 to 10 milliseconds it will respond, but some delay will be introduced by measurement and control circuit. So because of this control and the measurement circuit, delay will be occur, but usually it will be response. Okay, if there is some problem, over voltage is there, then TCR will respond in about 5 to 10 milliseconds. Okay, so you know that millisecond, right? And then for this reason, response times are typically, okay, so from 1 to 5 cycle of supply frequency. Okay, so there's all about the TCR. So very important thing is harmonics. You try to see that, okay, order of the harmonics and then effect of harmonics and severity of the harmonic. But very important thing is how to control the voltage using TCR. When you will employ the TCR, okay, you have to know that when you will employ the TCR, and then when how to control the TCR working principle, and then all little bit you can revise, but this one don't worry about this principle of operation, it will be taught in power electronics and application in detail. Okay, so you very important thing is we have to know how to control the voltage, and this type of control of is known as phase control system, which means depending upon the conduction angle, then you will fire the thyristor and then you control the voltage. Okay, this is a basic which you have to know. Okay, so that's all for today. And then if you have any doubt, and then if you really want to know about the harmonics, okay, so I will take one lesson, so if everybody agrees, some basic of the harmonics whenever we have a time. Okay, just now you know that there are different order of harmonics: third, fifth, 7, 9th, and then 11, 12 order. So but in this year, how to remove this harmonic third order, and then all by different arrangement of the this year 6 pulse this year and then 12 pulse this year. So 6 pulse this year can remove third and 9 order, whereas 12 pulse can remove the fifth and 7 order, and then lowest it has been left is 11 and 13. It cannot eliminate whole harmonic, at least there will be a harmonic, but if you left at 11 and 12, this can be easily filter out using simple capacitor bank. So this is how we carry it out. Okay, so that's all for today. Okay, so if you have any problem, okay, so you can share here, or if you don't have problem, so thank you for coming online. Okay.
Thank you, sir.
Thank you, sir.
Okay,
Thank you,
very
sir.
important thing is how to control is a must. Okay, and then operation part. Okay, this working principle you will learn in power electronics application, but little bit. So I'm not saying reject it completely. You have to see this. Okay, so that's all from my side. Thank you for coming online.
Thank you, sir.
Okay, so regarding harmonics, so I will, if there is time, one suitable time, I will explain about I will take 1 hour lesson on the harmonics. Okay, particularly, so if you join back, so I will take one lesson or maximum of 1 hour in harmonics. Okay.
Okay, sir.
Okay, so thank you for coming online.
Thank you, sir.
Yes, sir.
Thank you, sir.